magnetic ring, okay, having some cross-sectional area, say A, and say it is having internal diameter 10, external, and this is external diameter, say 12, okay, and this is a square bar of which the circular ring is made. Clear? Okay. So this is 10 centimeter, external is 12, and having cross-sectional area of a centimeter square. Okay. Clear? Okay. And we have wound number of turns over this. Say that N is say 200 turns, and say the current flowing through this is say I equals to say 2 ampere. Okay, and you have to find a flux that will flow through this iron ring. Okay, the square bar of iron, and mu r is say 300, something like this. Okay, so you have to find what will be the flux produced. Okay, so only, or you can neglect this information. It is a circular ring having internal diameter 10 and external diameter 12, is made from a square bar, of iron. The relative permeability is 300. Current and wound with a coil having n number of turns, that is 200 turns, and current through the coil is 2 ampere. You have to find the value of a flux. Okay? Can you do? Okay, being the first example, I will say first you have to calculate MMF. MMF is N into I, or there are alternative formulas, H into L. Clear? Now you have got 200 turns and 2 ampere current. So MMF is 400 ampere turns. Now this is the MMF. How will you get the flux now?
First we calculate reluctance, then
reluctance, it is a single circuit. No. So reluctance S. How do you calculate? L upon mu A. Or you can put L upon mu 0 mu R into A. Clear? Now what is the length of the path? How will you get? This is a circular ring. So this one, see, this is the bar shape. Clear? Okay, and this is bent into a ring. Okay, this is bent into a ring with internal radius 10 and external radius 12 centimeter. So what will be the length now?
Excuse me, sir.
R minus R.
Can you unlock the meeting? Like someone's trying to join because the network issue. She couldn't join. Can you?
No, everybody. See, I have to handle so many students. You should keep your alternative network available.
Can you? Sorry, sir. There are network issues.
Can't repeat everything because. So now reluctance. What will be the length? Just wait. What will be length of this circuit? See, this is the circular ring. So what will be the length of this circle? Pi d. Pi d are 2 pi r. Now this, either this or this. This has to be a mean length, mean value or average. Now you have an internal diameter 10, external diameter 12. So this is 10
Excuse me, sir.
and this is 12 if I talk. Clear? Now this is 10, this is 12. So what will be the D? You have to take the average of that, or you can take the average of a radius. So it will be 2 pi. Now internal is 10 centimeter and external is 12. So you have to take the average of these two, and it is a centimeter. Basically, we are working with a meter, SI system. So it will be 10 raised to minus 2 centimeter to meter. Clear? So calculate this length. Calculate this length. And tell me in a oral form or a. So this will be the length. And now what will be the area? What will be the area? It's a square bar. So 10 and 12 indicate that the length of the bar, this whatever you call, say, it's a square bar. So one side is 12 minus 10, that will be the size. And this, it's a square bar. So square of the side is the area, cross-sectional area. So, and that is also in centimeter square. So convert it into a meter square, it should be 10 raised to minus 4. So that gives you so many meter square. This is meters. Okay. And what is mu zero? Mu zero is 4 pi 10 raised to minus 7. And mu r is 300. So now you can calculate the reluctance. Okay. And after getting reluctance, you can take MMF upon reluctance is my flux. So do this process and tell me the answer. Okay, I will wait for 2 minutes. Hello, audible or not?
You are, sir.
Yes, sir.
Okay, so find out the value of flux which will be in Webers. In short, we put WB. Now,
It's 0.458.
0.89.
It's coming 11 by 24 hours. Sir, flux is 872.72 Weber, sir.
870
2.72.
Webers.
Sir.
Sir,
Don't think
8.72
there is
fine.
some problem. Don't think so.
So 8.72 into 10 to the power minus 5 Weber.
Yes.
Yes,
What
sir.
you say is real 8.72
72
to the power 10 raised to the power
minus 5.
minus. It's okay then. It's so much Weber. Okay? Clear? Now this is there. Okay? So what are the values here? What is the, you have to take the average or mean length. What is this? This meter, how much is the length?
Approximately 0.7
0.69.
meters.
0.699.
691.
999.
Okay.
Sir,
And what about,
0.225 we can write as well.
and this is 4 into 10 raised to minus 4.
Minus 4.
10 raised to minus 4. Clear? And putting all this value in this formula you get. Okay. Now this is one part. Now what I do, I make an air gap or just make a crack in this ring. Okay. So say I made an air gap of just say 1 mm, very slack, like a crack in a ring. Now what will be the flux, new value of a flux with an air gap? Now you will have a two circuit. One is, I will draw this. One is iron path and another is an air or air gap. Clear? So you have two circuit. You can solve it like a battery or electrical circuit. So this is my MMF. This is reluctance SI. This is reluctance SA. And now you can find out the flux phi. Okay. Now what will happen? They are in series. So reluctance, you can apply electrical laws. So total reluctance S total will be SI plus SA. Again, MMF remains same because same current, same value. Only I made a crack of 1 mm in a ring. Okay, clear? So either you can continue with this length because 1 mm in a 70 centimeter doesn't affect much. If you can allow that much error, you can take the length equal to this, or you can reduce it by 1 mm if you want to be more accurate. Clear? So you calculate now. What will be the reluctance for air gap SA. It is L upon mu A. Okay. Now mu R for air gap or non-magnetic material is 1. So whether it's a multiplicative identity, so you need not to worry. You can take directly mu 0 as mu for air or a non-magnetic. So your air gap is 1 mm, no? So 1 mm means 1 into 10 raised to minus 3 meter. Is it okay? And what is mu r? 1. So mu 0 is 4 pi into 10 raised to minus 7. If you wish, you can multiply it by 1. It's a mu r value. And now you can take air gap area equal to the ring area. Okay. So air gap area equal to the ring area. What is that? 4 into 10 raised to minus 4. Okay. So now you can calculate what is the reluctance of air. Nikalo? This is into this length upon mu 0 into area. What is the length?
Six 6.25 into 10 to the power
6.25 into 10 to the power
6.
6. Am I right?
Yes, sir.
10 to the power 6 positive. Clear? Now, okay. Now, what will be the total S reluctance? We can take SI because there is a slight change that 1 mm if you neglect. So this will only change. So you can take the reluctance value same as previous. What was the SI that time? Previous value you can reuse, doesn't matter. 1 mm doesn't affect in 70 centimeter. Little error we are introducing, but okay, doesn't matter. What was the value?
4.58 into 10 raised to 6.
4.58 into
10 raised to 6.
10 raised to 6. Pakka?
Yes. हाँ sir.
4.58 into 10 raised to 6. Clear?
Yes.
So now, okay, actually in reality, when you subtract 1 mm from this, little bit less, but doesn't matter. 4.58 plus 10 raised to 6 both, na? This is also
Yes, sir.
10 raised to 6. So 6.25, commonly I am putting 10 raised to 6. So what is the value?
Yes, sir.
Huh?
The
The essay
reluctance of
comes
air
out
gap
to be
is different, sir.
1.98.
1.99 into 10 to the power 6, sir.
2
Which
into
one?
10 to the power 6, sir.
So
No.
That's 6.25.
Wait. What is the reluctance of a iron? Is it correct?
Yes, sir.
Yes, sir.
And what about this air gap?
So it's
That is wrong.
1.98.
Huh?
Yes, sir.
1.98.
Not 6.25.
No, sir.
No, sir.
अरे कैलकुलेटर होते हुए भी इतनी गलतियां करते 1.98.
Sir, he forget to
Okay, now
Yes, sir.
pi, sir.
it is 1.98. Clear? So what is the total value? It may be 6 point something. निकालो
6.56. 0.56 into 10 raised to power 6.
6. Okay, 10 raised to the power 6. Now what will be the MMF? MMF remains same. So what will be the new flux? Say phi dash. I put it a phi dash. So it is 400 divided by 6.56 into 10 raised to 6. कितना आता है?
It's 6 into 10 to the power minus 5.
हाँ?
It's 6 into 10 to the power minus 5.
I think. और कोई दूसरा?
6.6 into 10 to the power minus 8.
to the power minus 5.
0.09 10 raised to power minus 5 or 6.
5, sir.
5.
Okay. Actually, what I was expecting, it did not happen. Okay. But you see, even a small air gap of 1 mm in 1 meter length, you see, it is getting reduced from 8.72 to 6. So in a magnetic circuit, a small crack or air gap will make
Significant
reduce
flux
the
change.
flux. Huh?
Significant flux change, sir.
Flux change, or you need more MMF to maintain the same flux. Clear? You need to produce high level MMF, more MMF to maintain the same flux, even if there exists a small air gap of 1 mm in 1 meter or so. Clear? So air gap increases the MMF requirement or reduces the flux significantly. That was the intention. Clear? Okay.
Yes, sir.
Now I give you one example. This just you try now itself. I have this type of a circuit. ऐसा circuit है? Clear? I can have 2 air gaps. I'll just make 2 air gaps. इधर क्या? I have put N is say 200, current I is say 5 ampere, this M 5 mm millimeter. Also same this millimeter air gap on 2. Okay, and see, I'm taking now average length. You have to come to this center and this center. So this average length is say 15 centimeter. And this also the average length, average center of this and center of this. So that is taken out. I'm not doing it every time. First example I took. So it is a mean length or average length for this path, say 30 centimeter. Okay, find out the flux. Find out the flux here. क्लियर? अभी ये सब काम आपको खुद करना है. आई विल वेटिंग फॉर आंसर्स. करो. And whoever solved it first, put his answer in a chat. Her answer in a chat. करो, शुरू करो. Do it fast.
Sir, what is permeability of core?
See, there are two data missing. One is permeability, say 500, and I did not tell you, you can take the, now we have, okay, time है वैसे. Okay, the cross-sectional area is 6 centimeter square कर देते, 6 centimeter square. Cross-sectional, you can assume same cross-sectional area for all the paths. Okay, 6 centimeter square. Chalo, and now find the flux value. Okay, we'll wait for more. See, I'm getting different answers from different students. Okay, so let us see. You have to first find the length. I'm just drawing what you can call geometrical lines. So you see, this is 15 and this will also be a 15. Okay, and this is 30. So this is also going to be a 30. We are assuming rectangular like that. So total length of magnetic circuit, or you can see the iron path. Okay, so what we'll do now, in between that there is a air gap of 5 mm, 5 mm. So from this we will minus that total air gap later on. Total length of iron is equals to twice 15 plus 30. This is 15, this is 15 twice, so 30 is minus 5 millimeter plus 5 millimeter. So it is 0.5 plus 0.5, all this in centimeter. So what length you get? Approximately 45, 90 means 89 centimeter. Okay, 45, 90. So it is 0.89 meter. Clear? You got this? Okay. Now air length is length of air is 1 centimeter. That is 0.5 plus 0.5 centimeter. So that is 1 centimeter. You got this. Okay. Now you calculate now what will I do? I'm taking say okay, air length. Now what will be the MMF? MMF is N into I. Okay. So N into I is 200 into 5, so 1080. Clear? Like this. Now what will be the reluctance of iron? Reluctance of iron is, I'm not putting the formula every time, so it is 0.89 upon, it is 4 pi 10 raised to minus 7, that is your mu 0, that is constant, into relative permeability is 500, relative permeability is 500, and what is area? 6 centimeters square, so 6 into 10 raised to minus 4. This is 10 raised to minus 4. So that is iron reluctance. What will be the reluctance of air? I am taking both gaps together. They are in a series form. Okay. So it is 1 centimeter. So 1 into 10 raised to minus 2 upon 4 pi 10 raised to minus 7 into mu r will be 1 because it's a non-magnetic gap, into, we are again assuming same cross-sectional area, 6 into 10 raised to minus 4. So this way we will get the reluctance of air path and reluctance of iron path. After calculating this, you can add total reluctance as S I plus S A. Clear? So after doing this, you can get the flux value as MMF is MMF upon total reluctance, and you can get it. Clear? So this will be your Weber's. So if I don't, you have to do the calculations and get the final answer. I am assuming that since 3.22 into 10 raised to minus 5, many students have given these answers. I don't agree or confirm.
6.49.
Somebody is saying 6.49. So it's a calculation that you have to do correctly. Clear? I'm not going to do calculations in the class. So assuming that if this is correct, you follow this process and do it. Okay. So this is about,
Excuse me, sir.
huh?
Can you please tell how to calculate length once again?
What for length you need to calculate?
So the total length.
Total length you need not to calculate. You are calculating reluctance separately. For air gap,
No, sir. Before that.
before that, I'm not getting you. See, you have got this a single line diagram or just plain diagram. This is 30, this is 30. And this is 15, 15. So I put them together and multiply it by 2. And from that I am subtracting air gap. So I get this length, which I will be using for calculating the reluctance of the iron path. Because both are of the same material. If this is of different material, then differently you have to calculate. Let us say this ring, this part, half part of this. Okay, this is of different material and having different, say mu r 2. then you have to separate. There will be 3 circuits now. You see, this is for A gap I will taking as a B, and this is my C part. So you will have 3 reluctances, A, B and C for this. Because it is of different material, it will form the. It is of the same material in this case, that's why I have added A and C together, and B, 2 B's are added together. Clear? And you can apply electrical like laws and you get the flux value. Clear? So you have to do this calculation. I am taking it because many students say in a chart box that this is the answer. You have to do the correct calculations and get it done. Okay?
Yes, sir. I was asking the same. Thank you.
Huh? You were asking?
The same, which you explained it just now. Thank you.
Okay. Now, till this time, we were assuming the air gap. There is a term we must learn. We call it as a fringing. Fringing effect. Or if just fringing normally, effect word may not be there in a book. So what is fringing in magnetic circuit? Huh? What is fringing? किसी को मालूम है? Anybody having knowledge?
So collection of magnetic lines in a particular area, accumulation of magnetic lines.
Fringing effect, no. No. See, this is my ring. ठीक है? This is my ring. ठीक है? Now what I did, I made an air gap. Okay, somewhere here I made an air gap like this. Okay. But while doing calculations, okay, like this. While doing calculation, we are assuming that the cross-sectional area of an air gap, cross-sectional area of an air gap, we are assuming same as that of this iron path. Iron means not metal, it's a magnetic path. Okay. So cross-sectional area of an air, we are assuming equal to the cross-sectional area of iron path. Okay. It may be any magnetic material. It is not just only iron as a metal. It may be cobalt, something like that. So it were assuming, but that is not the fact. Actually, when the flux is passing through it, practically what actually happens, it bulges out like this. The flux, when passing through air gap, it doesn't follow this path, it bulges out. So the effect is its cross-sectional area of air get increased little bit. Okay? Practically. Understood? It bulges out in an air gap like this. So the effective cross-sectional area of an air get increased, and that effect we call it as a fringing effect. Okay, so till here, now if there is, if you want to consider the fringing effect, let us say here. So here, this area, what is that? Sorry, this was the area which we are assuming. It might get increased to 6.2 because of the fringing effect. Clear? Understood? Now, that will affect the reluctance of the air. समझ में आया?
Sir, Yes, sir.
So that we call as a fringing effect. One thing. So effective area may be 1.1 times or 1.05 times, something like that. There is a little increase in the effective area in an air gap. Now there is another term what we call as a leakage factor. Leakage factor, or a leakage coefficient also sometimes called. Normally lambda is the symbolic notations. Okay. Now this is equal to, okay, total flux generated or developed, you can take, divided by useful flux. Okay, that is the formula. Now its value ranges up to say 1.1 to 1.25 practically, this value. The leakage factor value ranges from 1.1 to 1.25. It's a nominal, it's typical value. It may be maybe 1.01 also, or it may be 1.4 also, depends. But this is the normal range in which it may vary. समझ में आया? So the leakage factor is a ratio defined as total flux divided by useful flux. Now what is useful flux? Total flux is the flux generated by the MMF source, that is coil. Okay, so whatever flux is expected are developed or generated by this coil, that is a total flux. But as I told you, there exists थोड़ा सा digital board करो. See, what we are assuming that whole of the generated flux is passing through the path, but that is not the case. Flux may have this path, it may have this path, and these are not the flux which are doing useful work. So the useful work is the flux flowing through the intended path. Intended path is a useful flux. Matlab, what we expect that flux should flow through this path. This is our intended path. But all the generated or developed flux is not following this path. Some flux lines will be following this, some may be following this, some may link like this. So this is the leakage flux. Okay, these are the leakage flux. So leakage flux and the useful flux will be the total flux. Sum of the leakage plus useful is a total flux. Clear? So total flux will always be more than the useful flux. Okay, what is useful flux? Flux flowing through the intended path. जहाँ हमारी इच्छा थी कि वो ऐसे फ्लो हो, वैसे उस पाथ से हो रहा है, तो it is a useful flux. Understood? So leakage total flux divided by useful flux. So now if leakage factor is 1.1, clear? And say, I'll tell you, and let us say, just for understanding purpose, let us say the flux in an air gap, which is air gap, is say 1 Weber. Clear? I have put a coil here, and 1 Weber is the flux in an air gap. Clear? Now forget about the fringing. So 1 Weber is the flux passing through this air gap. And if a leakage factor given is 1.1, that means the flux flow or generated flux will be 1.1 times. Okay, so the flux in the air path is 1 Weber, and in the iron path it will be 1.1 Weber multiplied 1 Weber multiplied by factor. So that gives you 1.1 Weber. So I hope you understood what do you mean by leakage factor or leakage coefficient. Understood? I hope.
Yes, sir.
Okay. So all the flux generated may not reach to the intended path, just useful or expected path. It may have some leakages because, as you know, magnetic flux doesn't have perfect insulator even today. Okay. So this is about the leakage factor and this. That means if now, okay, 5 minutes. Just conceptually, we will understand what do you mean by this. Say, I already told you. Say, I'll give you just if you can try it at home or otherwise we will repeat tomorrow. Say, this is my ring, some cross-sectional area will take, say 4 centimeters square is a cross-sectional area, and here I have an air gap. Okay, and the flux here in the air gap is say phi is 1.1 Weber. Okay, and the leakage factor is 1.1. Clear? So I want an air gap flux of 1.1 Weber. You can neglect the effect of fringing. Okay. And there is a leakage factor of 1.1 Weber. And I have, you can assume that I want to generate a 1.1 Weber air gap flux. Leakage factor is 1.1 and it has turns of say 300. So you have to find out how much current you need to flow so that flux generated in an air gap is 1.1 Weber. You can take mu r as say 300. Okay. And the diameter of the ring, I will give the mean diameter. Mean diameter is say 20 centimeter. Mean diameter is 20 centimeter. Clear? It's a diameter, 20 centimeter mean diameter. Okay? And the cross-sectional area is 4 centimeter square. And air gap, say, 1 mm. 1 mm air gap. Okay? And I want to produce a flux of 1.1 Weber in this air gap where the leakage is given as 1.1 factor. And the turns are 300. So you have to find how much current I need to flow through this so that these conditions are met. Okay? You can take this as a homework and solve it. Okay? So next class, I will expect the answer from you. Okay? Understood?
Yes, sir.
Difficulty hai? Okay. So now we stop.
Okay, sir.